Physics 12, and welcome back to week 3 of electrostatics. Today we are going to be covering Coulomb's law, which is the law that determines the force between electrostatic particles, or basically electric particles, and this is the law that describes it. So it's essentially this law we've seen before. We've seen the formula K Q1 Q2 over R squared. It fits into our square on the bottom right hand side. So we have field and force down here. If we're talking about point charges, it's going to be over R squared, whereas these two are over R. And because it's on the right hand side, it'll have a Q1 and Q2. Okay, so this is our force. First thing I want you to do is, just to get you started, can you compare the gravitational force and the electric force between an electron and a proton? So this is all the information you're going to need. This is the mass of a proton, mass of an electron, our universal constant g. We're still going to say that the radius is, in case you haven't seen this unit before, a 10 to the minus 10 meter. This is called an angstrom, and it has this weird symbol like an A with a circle on its head. And this is about roughly the atomic radius of a hydrogen atom. So if you have a hydrogen atom, the electron is about 1 angstrom, or about 10 to the minus 10 meters from the nucleus. And then we've got the two charges here. So charge of proton, charge of electron, and K, this universal constant that we have. So pause the video here and calculate those two values for those two quantities. Okay, well, I'm sure you're back now from calculating that, so let's see what we have here. So let's do the gravitational force. So it's going to be 6.67 times 10 to the minus 11 multiplied by the mass of the proton, 1.67 times 10 to the minus 27, multiplied by 9.11 times 10 to the minus 31. That's the mass of the electron. We're going to take that divided by 1 angstrom squared. Okay, and that gives us around 1.0 times 10 to the minus 47. I'm just going to leave that here. Okay, so force of gravity around 1.0 times 10 to the minus 47 newtons between the electron and the proton. That's a pretty small amount of force. Okay, let's take a look at the electrostatic force. So in this case here, we're going to have our K, so 9 times 10 to the 9, K times Q1 times Q2. Now Q1 and Q2 are both the same, so I'm just going to put times 1.6 times 10, times 10 to the minus 19. I should put my brackets in there. I'm not exactly sure if it would work with or without brackets with the squared unit there, but we'll just put it in there to be careful. And then we're going to divide this by the 1 angstrom. Okay, and that gives us our electrostatic force is going to be around 2.3 times 10 to the minus 8. So if you take a look at these two values here, don't worry too much about the 1 or the 2.3, but the force of gravity between those two would be 10 to the minus 47, and the electrostatic force would be around 10 to the minus 8. So you can see that the electrostatic force between subatomic particles is around 10 to the 39 times greater. So the electrostatic force is 10 times 10 to the, or 10 to the power 39 times greater than Fg. So Fg, it's funny, one of those, people often say that force of gravity is the weakest force, and if you compare it to the force, an electrostatic force between a proton and electron, yeah, it's 10 to the 39 times smaller. And that is really, really small. But don't let that deceive you, because ultimately the strongest force in, what's able to produce the strongest force in the universe is gravity as well. If you think about a black hole, that is as strong of a force as exists anywhere in the universe. So the one thing that kind of can make gravity ultimately much, much stronger is that it's always cumulative. So if you have a bunch of electrons, you can't put a bunch of electrons closer together. They're always going to repel each other. Whereas you can just keep adding mass and adding more mass, and that's essentially how we get a black hole or a neutron star or something like that. So you can always put more mass in, but you can't always add more charge. It's always going to repel the other charge, and so you can't ultimately get one-sided electrostatic force. Just an interesting point to consider. Nothing that you're going to be tested on or anything, but just an interesting fact for you. Okay, there we go. And also, I didn't mention this before, but the unit for K is going to be very similar to the unit for G, except we're just exchanging kilograms for coulombs. Okay, let's carry on. So, next bit here. So what does this tell us about the relative strength? Well, we just kind of discussed that right here. So what this says to us is that at least in this situation where there's a proton and electron, electric force is much, 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 much greater. Okay, let's try some example problems of this equation here. So the first equation is we're going to compare, again, we're going to make a quick comparison to gravity. If we have two students that are 1 meter apart, and then we give them some charge. So with this question here, this is to do with gravity, this first one here. The second one here on the bottom, they have a charge of 2 millicoulombs each. What's the force between them? And this third question here, 2-point charges are producing a force. What's the distance between these two? I'd like you to pause the video now and try all 3 of these problems, but maybe not the fourth one. I'll discuss the fourth one with you before you go. So please pause the video. Please try these problems out to give yourself some practice. Okay, well, welcome back from your pausing and solving. Okay, let's try these problems out here. So the first one we have is the force of gravity. So we know this is our formula, Fg equals G m1 m2 over r squared, and G is 6.67 times 10 to the minus 11 multiplied by 85 times 85. That's the mass of both students, are the same. And we're going to divide this by r squared, so divided by 1 squared, and what do we get? 6.67 times 10 to the minus 11 times 85 squared, and divided by 1 squared is just divided by 1, so the same answer. So the gravitational force, if you got 2 students, 85 kilograms, and they're about 1 meter apart, there is a gravitational force. It's around 4.8 times 10 to the minus 7 newtons. So extremely, extremely small. You wouldn't even be able to feel that, essentially. It would be impossible to detect, except with maybe the most high-tech devices in the world for detecting force. So let's take a look at the next one. If we each have about a charge of 2 millicoulombs, so this is kind of giving you an idea of how much a millicoulomb is. So let's take a look here. Each of these students has a charge of 2 millicoulombs. What's the electrostatic force? Well, we know our formula is K Q1 Q2 over R squared, and this is going to be 9.0 times 10 to the 9 multiplied by 2.0 times 10 to the minus 3. I'm just going to say squared. They both have that, so times itself, and divided by 1 squared again. So let's check this out. 9 times 10 to the 9 times 2 times 10 to the minus 3 times 2 times 10 to the minus 3. And let's see what we get. 36,000 newtons. So if a newton is roughly the force it takes to hold an apple up, you can see that that would be a huge amount of force. So what this is telling us, hopefully what you're picking up by that, is that 1 millicoulomb is actually still a huge, huge, huge amount of charge. If we say like a lightning strike is maybe between 1 to 3 coulombs, this, even 1,000th of a lightning strike is still pretty a large amount of charge. So hopefully that's impressed upon you there. And then the last question out of these 3 is 2-point charges. Here's the charges given. This is 1.8 microcoulombs and 2.4 microcoulombs, and this is the force, and we're trying to find out what is the distance. Well, our formula again is going to be Fe equals K Q1 Q2 over R squared. We're trying to solve for R squared in this case. So I'm going to multiply both sides by R. By R squared, and that will cancel out. I'm going to divide both sides by the force, so divided by the force. Actually, I'm just going to put it underneath here, so divide by the force. That way these are going to cancel out, and this is what I have here. R squared equals K Q1 Q2 over F. This is going to equal to 9.0 times 10 to the 9. Multiplied by 1.8 times 10 to the minus 6 and by 2.4 times 10 to the minus 6 and divided by the force, which is 2.2 times 10 to the minus 3 newtons. And our answer for that is 9 times 10 to the 9 multiplied by 1.8 times 10 to the minus 6 multiplied by 2.4 times 10 to the minus 6 and divide that by 2.2 times 10 to the minus 3. And this gives us 17.67. So just be careful, this is our R squared value. So our R squared value is 17.7, and so we take the square root of this answer and we find our R equals 4.2 meters. So this is our final answer for the third question here. Hopefully that's what you got as well when you tried it yourself. Okay, so what about this one here? So we're getting a little bit more complicated. Now we've got three different charges. So charge number one is this 1.7 microcoulomb charge. Now I left it as microcoulombs because I really want you to start to, you're going to see these units the rest of your scientific career if you go into any sciences in university at all. They're going to be using these standard units here. So microcoulombs, remember this is going to be, so millicoulombs is going to be times 10 to the minus 3, microcoulombs is times 10 to the minus 6, nanocoulombs is times 10 to the minus 9. Okay, so this is my first one here, 1.7 times 10 to the minus 6, and this is 2.0 times 10 to the minus 2 meters, so 2 centimeters. And then we've got 2.5 microcoulomb charge, the 2 centimeters away. And then we've got 3.5 centimeters, or times 10 to the minus 2 meters. We've got a charge of minus 2 microcoulombs. Okay, so what's the net electrical force? Well, to think of that, we have to do these. I would suggest doing these as a vector addition problem. Luckily, they're all in a straight line. So if we think about this one here, we've got this positive charge here and positive charge here. So I'm going to call this let's call it F2.5. So we'll, and what direction would F2.5 be? I want you to think about that. What direction would F2.5 be, the force caused by this Coulomb? So I'm just going to use this subscript. And then there's this force over here, which I'm going to call F minus 2, because it's the force from the minus 2 microcoulomb charge. So you have to think about these two forces first. What direction are they going? And then how are you going to add them up, taking into account the direction? So please pause the video here and come back once you've solved the problem. Okay, so the problem is, what is the net force on this charge on the left-hand side? So let's add up what are these forces. So F2.5 is the force caused by this. Now this is positive, so that means this is going to be a repulsive force. And we can calculate what that is. We also have this other force here, which is caused by the negative 2 microcoulomb charge. Well, positive and negative is going to attract, and so there's going to be this force here. Now considering this charge is smaller in magnitude than this, and considering it's further away, we can probably guess right away that this is going to be the smaller of the two charges, this F minus 2. But let's calculate what those are. So F 2.5, so F net electrical force is going to equal F 2.5 plus F negative 2. Now F 2.5, this is where, and I've had a few students asking me, when do we worry about negative? When do we worry about positive charges? When should we be thinking about that when we're doing our calculations? And the answer is, in a sense, it's up to you to figure out the directions of the forces. I would say is probably the best way to answer that. So in this case here, for F 2.5, I wouldn't necessarily plug in their positive and negative charges. I would just plug in the fact that this is going to be a negative value. So this is going to be negative, because it's moving to the left, of whatever this force is. So K, Q1, Q2.5 divided by R squared plus, I don't know what happened there, plus F negative 2. So I'm not sure why that disappeared, but I guess we can just plug in the numbers. That was a weird glitch in the matrix. Okay, so this is going to be negative 9.0 times (10 to the minus 9) multiplied by Q1, 1.7 times 10 to the minus 6 coulombs, multiplied by 2.5 times 10 to the minus 6 coulombs, and I'm going to divide that by the distance, and the distance here was 2.0 times 10 to the minus 2 squared. And I'm just putting this negative sign at the beginning to remind me that it's going to the left, and I'm going to add this force here. So this is going to be, again, 9.0 times 10 to the 9 multiplied by 1.7 times 10 to the minus 6 multiplied by, I'm not going to worry about the negative 2 in the charge, I'm just going to put in the charge here because I've already taken into account the fact that it's going to be to the right or positive, as opposed to this one, which is going to be negative. And I'm going to divide this by 3.5 times 10 to the minus 2 meters, all squared. So I'm not going to do the calculations on my calculator. That's going to take too much time, but I will say that it's going to be 71 newtons overall. So I'm not going to go through the work on my calculator. You can plug this in yourself. It should come up to 71 newtons, and then the question you have to ask yourself is, what's the direction? Well, this one here is going to be a larger of the two force. I guess when you calculate this, you're going to come up with negative 71, and so that's going to tell you, in other words, it's 71 newtons to the left. So again, with the signs, if you're looking at these types of problems where you're adding up the forces or subtracting the forces, if you're dealing with essentially with vector addition problems, don't worry about putting the signs into your formula. Just keep track of the direction and treat them as vectors. For example, if I look at this problem here, let's say I was trying to find out the force on the 2.5 microcoulomb charge. Well, then this would be a positive force and this would be a positive force. If I do it here, this would be a negative force and this one would be a negative force. But we're not too worried about whether or not the values would be positive. If I plug in this and this, it would end up giving me a different sign than this and this. So for example, if I multiply these two together, I'm going to get positive, which is correct. If I multiply these two together, I'm going to get negative, which would be incorrect because it is going to be going to the right. Hopefully I didn't throw you off. If you need to replay that and listen to what I said again, feel free to do so. So next week we're going to look at situations where the forces may not be lined up at all. So if I'm trying to find the force on this and this is positive and negative, well then just plugging in the formulas isn't necessarily going to help us, but treating these as vector problems. So this plus this gives us an overall force in this direction. So we're going to look at that more next week, make it a little bit more complicated than it is now, but we've done vector addition before. We've seen how to add up two forces that are at different angles. We've been doing that since grade 11, you've been adding up vectors. So should be nothing new. I will say when you're adding up scalars like potential or potential energy, then that would be a good time to think about signs, because we don't need to think about positive and negative in terms of the direction of the arrows, but you will need to think about positive and negative in terms of, is this a positive potential, is this a negative potential. But for the purposes of adding vectors, fields, or forces, I would simply ignore the signs in the equation in terms of the charges, and I would keep track of the direction of the arrows. That's going to be the best way to make sure that you're getting the answers correct. So, if you have any questions, again, please don't hesitate to email me, and I hope you found this video informative.